Okay, so we're all done with conservation of mass for control volumes. Next topic will be conservation of energy for control volume. So we've already talked about conservation of energy for a closed system, and now we're finally moving on to conservation of energy for a control volume. Also in this class, conservation of energy has a name. It's called first law of thermodynamics. Let's recall. If you have a closed system like this, piston cylinder assembly, and it's closed, there's no inlet, no outlet, and the gas inside is your system. This is a closed system. What is the first law that we introduced? The equation we give you is Q, heat transfer, minus W, work, equal to delta E. That's the first option. Option number two, divide every term by time. So Q dot heat transfer rate minus W dot power equal to derivative E over dt. Okay, so this is conservation of energy equation or first law of thermodynamics for a closed system. And now we're going to talk about what if you have a control volume. So for example, you still have piston cylinder assembly. However, you have an inlet and also an outlet, and this is your system within the dashed line. In this case, your system is a control volume because you deal with an inlet and outlet. This is a control volume. If that's the case, what will be the first law? Okay, so will we still have heat transfer? Yes, you still have heat transfer. Let's keep that term. Do you still have work? Yes, because you may still push up the piston or get pushed, so you still have work. And then what you have in addition compared to a closed system is the inlet and the outlet. So what happens at the inlet? Fluid goes into the control volume. And what does the fluid bring? The fluid carries energy going into the control volume. So we need to add one more term. We call it EI. What does EI mean? Total energy carried by the fluid, which is added to the control volume. So plus EI. And then we do the same thing for the exit, but this time it should be minus EE. What does EE mean? The total energy taken away by the fluid at the exit. So that's why it's minus sign. And then right hand side still the same as before, delta E. This E is the total energy of your control volume. Alright, and then usually when we deal with the control volume, we divide every term by time. So this becomes Q dot minus W dot plus EI total energy dot minus total energy EE dot right hand side over dE over dt. Right hand side is dE over dt. Okay, so now let's do this. Q dot minus W dot. Alright, so now we're gonna rewrite EI and EE. First of all, plus EI, EI. What is EI? Capital E means total energy. So EI is the total energy brought in by the fluid at the inlet. How many components does total energy have? Do you remember? Yes, there are three. First one, kinetic. 1 over 2 mi over vi squared. That's kinetic energy. And then plus potential energy. MIGZI. This is potential energy. And then one more term for total energy, internal. Very good. MI lowercase ui. That's total internal energy. And don't forget it's EI dot with a dot on top of it. So that means divide every term by time. So mi dot, mi dot, and mi dot. So this is how you rewrite EI dot. And then we do the same thing to rewrite at EE dot. So minus 1 over 2 m dot E VE squared plus m dot E GZE plus m dot E UE. And right hand side dE over dt. Okay, m dot I is the mass flow rate at the inlet. M dot E is the mass flow rate at exit. VI is the fluid velocity at inlet. VE is the fluid velocity at the exit. ZI is the height of the fluid at inlet. And ZE is the height of the fluid at the exit. Okay, so we're almost there. This is the first law, conservation of energy equation for a control volume, but we can further simplify this equation by rewriting W dot. So next question is, what is W dot? We're going to rewrite it. Okay, so now let's start from this setup again. You have a piston cylinder assembly, but keep in mind this time we're dealing with a control volume. So give it an inlet and give it an outlet. Okay, everything inside is your system. So draw the dashed line. And this time your system is a control volume because you have mass transfer. At the inlet, you have mass coming in. The mass flow rate is m dot I. At the exit, you have the mass leaving. We call it m dot E. Okay, and then we tell you the pressure of the fluid at the inlet is Pi. The pressure of the fluid at exit is Pe. Okay, so now we're going to rewrite W. Okay, so how many works can you find acting on the control volume? First of all, we still have the movement of the piston. So for example, if the gas will expand, it's going to push up the piston, generating work. So first term is W, but this time we call it WCV. This term comes from the movement of the piston. The movement of the piston gives you this term. And in addition to this kind of work, we have two more terms for work. What is that? For example, at inlet, the pressure is pushing the fluid into the control volume. So that is push something over a distance. Push something over a distance. What is that? That's the definition of work. So that's the second work we need to consider. Push something over a distance. How do you calculate work? Force multiplied by distance. Okay, force multiplied by distance. And what is the force at inlet? We don't have force, we have pressure. Pressure multiplied by cross-sectional area is equal to force. So we use Pi times Ai. Pressure multiplied by cross-sectional area of the inlet is equal to force. So PIAI gives you the force at inlet. Force multiplied by distance is work. So next we multiply PI with AI with distance. So let's call it DI, distance. Okay, next one, plus or minus sign. Okay, you push something into the control volume. So that is like you push the control volume. If you push the control volume at the inlet, control volume consumes this work. Consuming work, that's negative work. Okay, so PIAIDI with a negative sign. And then we do the same thing for the exit. This time is PEAE DE exit and plus or minus. At the exit, it is the control volume that is pushing the fluid out of it. If the control volume pushes, that means the control volume generates work. Generating work gives you a positive work, so plus sign. Okay? Alright, so now let's recall we're looking for W dot. What we're going to do is to divide every term by time. W dot equal to W dot CV minus PIAI DI over time plus PEAE AE dE over time. And let's take a look. What is distance over time? Distance over time is velocity. So we can rewrite this equation to W dot CV minus PIAI times velocity VI plus PEAE velocity VE. Okay, and then let's continue. W dot CV minus PIAI VI, and then what we're going to do is a math trick. Multiply this term by rho I and then divide this term by rho I. We do the same thing for the third term in our hand side. PE AE VE times rho E and then divided by rho E. Okay, so now why do we do this math trick? Let's take a look. Rho VA. Rho VA show up. And here, rho VA at the exit show up. Do you still remember what is rho VA? Yes, very good. Rho VA is mass flow rate. So we can rewrite this equation to W dot CV minus PI times rho VA can be rewritten to mass flow rate and is at inlet divided by rho I plus PE times m dot E over rho E. And then last step. Usually in this class we do not use density but the inverse of density. The inverse of density in this class is called nu, specific volume. So now we can continue to rewrite our right hand side. It becomes W dot CV minus PI m dot I, but this time rewrite 1 over rho I into nu I, so times nu I plus PE m dot E times nu E. So this is how we rewrite W dot, and then what we can do is to plug in this new expression of W dot back into our first law for a control volume. Plug in this new expression of W dot back into our original equation. And we do the algebra. It will be like this. Q dot minus W dot CV plus PI m dot I nu I minus PE m dot E nu E, and then plus 1 over 2 m dot I VI square plus m dot I GZI plus m dot I lowercase ui minus 1 over 2 m dot E VE square plus m dot E GZE plus m dot E UE lowercase ue. Right hand side is still dE over dt. And now let's take a look. This term has m dot I, and those three terms have m dot I. So we combine those four terms together by taking out m dot I. Q dot minus W dot CV plus m dot I. Take m dot I out of the four terms. It becomes PI times nu I plus lowercase ui and then plus 1 over 2 VI squared plus GZI. And next, let's take a look. This term has m dot E, and those three terms have m dot E too. So what we do is to take m dot E out of those four terms. PE nu E plus lowercase ue plus 1 over 2 VE squared plus GZE. And right hand side, dE over dt, still the same as before. And now let's take a look. What is P nu plus U? Do you still remember? P nu plus U. Okay, recall lowercase u plus P nu is the definition of lowercase h, specific enthalpy. Specific enthalpy. So now we can rewrite this equation to Q dot minus W dot CV plus M dot I, and now it becomes HI plus 1 over 2 VI squared plus GZI. And then do the same thing, minus M dot E. First term becomes HE plus 1 over 2 VE squared plus GZE, and right hand side dE over dt. Okay, so this is our final equation, first law of thermodynamics for a control volume. This is the first law of thermodynamics, which is essentially just conservation of energy equation for a control volume. Okay. All right. Next, I want to make a note here to help you in future. W dot CV, do not forget, W dot CV comes from moving parts in your system. So for example, if you have a moving piston, if the piston can move, then this term will not be equal to 0. However, if your system does not have any moving parts, then W dot CV must be equal to 0. Okay, next we talk about a very special case, and the special case is steady state. Oh, okay, I forgot to do one thing. So the third term in this equation here, the total energy brought in at the inlet. What if you have multiple inlets? You do the same thing. Sigma every inlet up. What if you have multiple outlets? You do the same thing. Sigma all the outlets. Okay, so that's the complete equation. First law of thermodynamics for a control volume. Okay, now let's talk about a very special case. What's going to happen to this first law of thermodynamics equation if the system is at steady state? First, you're going to have total mass coming in equal to total mass leaving. This equation comes from conservation of mass equation. If at a steady state, total mass coming in must be equal to total mass leaving. And then what happens to my conservation of energy equation, which is first law, is right hand side dE over dt must be equal to 0. Steady state means no property changes over time, and the total energy, capital E, is a property. So what is the change of capital energy, total energy over time? It must be equal to 0. Okay, so that's a special case.